I am Catherine Amstutz, and this is Physics Lab 4. The purpose of this lab is to analyze a video and create a model of the motion of the mass on an oscillating spring, and then to compare the predicted motion and the observed motion of the mass, which is done here, and to plot the energy changes, which is done here. This is a preview of my results. Some fundamental physics principles necessary to understand this lab are the energy principle and Newton's second law. The energy principle is the change in energy of a system is equal to work done by the surroundings. And when that work's equal to 0, which is what we're assuming for this lab, change in energy is equal to the change in kinetic energy plus the change in potential energy. For this experiment, in addition to kinetic energy, we are discussing spring potential energy and gravitational potential energy. We have here our kinetic energy formula, our potential energy formula for spring, and our potential energy formula for gravity on Earth. For Newton's second law, it's the usual force equal to mass times acceleration, and the velocity and position update formulas can be derived from that, and that's what we use in our code to create our models. The models themselves are an experimental model where we analyze a video using Tracker, and a computational model in WebVPython where we create a model and then compare results to our first experimental model. Here is our experiment video. Notice that almost all the motion is taking place on the y-axis. I did some analysis of the video to determine that our coefficient of stiffness for the spring is 7.17 newtons. I did that by finding the average period, which is t, and then plugging it into this formula. Additionally, since the magnitudes of gravitational force and spring force must be equivalent to cancel each other out, I found that the relaxed length is equal to 0.51 meters, and I found that using this formula right here. The system is the spring, the earth, and the block. Surroundings are equal to 0. They're not discussed in this experiment. The initial conditions include the mass of the block, the relaxed length of the spring, the direction the spring's pointing, the initial position determined by the initial observed position in Tracker, the initial velocity, which is determined based on the first two positions in Tracker and the amount of time between those first two positions, and delta t, which is a very small multiple of our change in time. The first part of the coding essentially is copying and pasting over those initial values that I just discussed and calculated, adding in the spring constant value, and then determining the kinetic energy, gravitational potential energy, spring potential energy, and total energy initially present in the system. For this loop, while t is less than 5.795, which is the max time observed in Tracker, we first set aside all of the values that were found the last round of the loop or in the beginning as initial energies. Then we find the gravitational force, which was always going to be the same, and the spring force, and calculate net force based on that. Then we use the velocity and position update formulas to update the mass's position and velocity. And then now that it's got a new position, we have to update the spring force, or rather the components that make up the spring force. Calculated the energy changes by finding the new energies with all of the new values calculated in the previous slide, and then subtracting our initial energies from our final energies. I then updated the time by adding delta t to our current t value. This is our computational model. So the blue represents the computational model data, while the red represents the actual observed data. And here are the resulting graphs. We have our change in energy versus time, our change in y position versus time, and our change in x position versus time. So some analysis. We'll notice that our data predictions oscillated much more wildly than our model predictions in both the x and the y direction. The x direction, it makes sense because the initial velocity for our x value was 0. So even though there was a little bit of fluctuation, it's really nothing in comparison to the changes in the y direction. Some potential sources of error are that there was no consideration of forces that could impact the motion of the mass at the end of the spring in the x direction due to that initial x velocity of 0, and that we had some propagation of error via iteration. The energy principle is satisfied because our overall change in energy is equal to the sum of the change in kinetic energy, the change in spring potential energy, and the change in gravitational potential energy. This is a graph of our tracker y values, and this is a graph of our tracker x values, both versus time. So the average period for the y value is much less than the average period for the x values, and that's because the y value is the actual fluctuating motion based on the opposing spring forces and gravitational forces, while the x values were just random and minor oscillations. As you can see, there's actually very little change. These y values are very small. In this experiment, I tracked the motion of a mass at the end of a spring, used Newton's second law and the energy principle to create a computational model of the motion, and compared the two models.